Hi, right now we're gonna study RBC metabolism and we're gonna understand something which is called 2,3 phosphoglycerate. Okay, so we're gonna study our RBC metabolism and we will study 2, 3 by bisphosphoglycerate. Okay, so it's called 2, 3 BPG. Very common. The main question here is that why. Let me write you why. What exactly is happening? The main question is why RBCs sacrifices ATPs to deliver more oxygen. Okay, so we know this fact. There's a fact. This fact is that RBCs like to sacrifice their present ATP levels, and they would rather have less ATP but produce enough oxygen, not produce but have enough oxygen so that they can maintain a good gradient levels of oxygen, right? So we have a lot to cover. To understand all of this, we want to understand RBC physiology, glycolysis, oxygen transport, hemoglobin, ATP production, Rappaport Lubring shunt, and enzyme specificity. We want to build on these topics, right? Now imagine the evolution is creating RBC, right? Just let's go into the topic now. Imagine the RBCs is being synthesized, right? Now what's the job of RBC? RBC job is to usually carry oxygen, right? But that's incomplete. There are two other jobs. The two other jobs is, first of all, it's not just carry oxygen. First is to pick up O2 at lungs. That's job number one. Second is travel to the target tissue and then drop off that O2 to the target tissue, right? So that's RBC, right? So what do you think? Which job, the job number one or the job number two, is harder? Which job is tougher for an RBC? What do you think? Turns out that for an RBC, the job number two is way tougher than the job number one, right? Releasing oxygen. That is tougher for RBC. Now think about it. Imagine hemoglobin grabs oxygen very tightly. Is that good? I mean, initially, yeah, I think, because lungs become very efficient, right? But now imagine that RBC reaches that target tissue, that target muscle. Will oxygen leave the hemoglobin? No, because it's holding the oxygen too tightly. The tissue would become hypoxic, right? And let's now imagine the opposite problem. Suppose hemoglobin barely holds oxygen. Now what's happening? RBC reaches the lung, the oxygen falls off immediately, and very little oxygen reaches your tissue, right? So therefore, evolution needs balance. The biology needs balance. And hemoglobin must bind to oxygen strongly in lungs and release the oxygen easily in the tissue. Now, how would you do that? How would you solve this major problem? Right? We need a balance. You solve this major problem by a regulator. This regulator is called 2,3 bisphosphate, not bisphosphate, 2,3 bisphosphoglycerate, commonly called as 2,3 BPG. This is the regulator that is responsible for your RBC cleanup crew and everything, So this is regulator. Now, before we even ask the question, what is this weird little enzyme, we wanna really think about RBC metabolism, right? First question: does RBC have any mitochondria? Well, no, and this is very high yield. Why no mitochondria? Imagine RBC had a mitochondria, right? We can imagine that. Now, what would mitochondria do? Use oxygen, of course. But the RBC job is to deliver the oxygen itself, not consume it. So evolution removed it, right? The God was like, okay, you don't want to give oxygen to RBC because RBC job is to remove it, right? To carry it from lungs to the tissue, right? So it's a cool design, I think. The result is that without mitochondria, how does an RBC make ATP then? Only one pathway remains. That is called glycolysis. Nothing else. No TCA, no oxidative, no beta oxidation, no alpha oxidation, only glycolysis. So only glycolysis helps RBCs, okay? So only glycolysis helps them, right? So let me put glycolysis here. So only glycolysis is helping Mr. RBC for ATP. Now, now you would think that why RBC even needs ATP, Now, if RBC don't contract, if RBC don't, do anything much, why do they need a ATP? I thought about it. Turns out that RBCs has these sodium potassium pumps, and these pumps are ATP based, right? We call them sodium potassium ATPases, right? So they have these pumps. So they have these sodium / potassium pumps, and they are ATPases, okay? So they use ATPases. That's important right there. So they need ATP for these pumps. That's the first thing, okay? Without these ATP, the water would get inside, right? And the cell would swell up and hemolysis will occur, right? What about other things like membrane flexibility? RBCs have to squeeze through these capillaries, right? And even though RBC is very small, like 7 to 8 micron in diameter, right? Still, you need to have ATP to maintain this membrane skeleton, like spectrin and ankyrin, right? That allows this remarkable deformability, right? What about rigidity and integrity, right? ATP supports these membrane, right? And this is exactly why RBCs can live up to 120 days, because it has glycolysis, okay? If there was no glycolysis involved, RBC would die earlier, okay? That's the pump. Okay. So now we understand a little bit about RBC. Let's come to glycolysis now. Right, let's talk about glycolysis. So this is our glycolysis right there. Okay, so what is glycolysis? Glycolysis is when you convert glucose into glucose 6-phosphate with the help of hexokinase or glucokinase, right? And then you turn that glucose 6-phosphate into something which is called as glyceraldehyde 3-phosphate, right? And then you turn this glyceraldehyde 3-phosphate into 1,3 bisphosphoglycerate, 1,3 BPG, right? And then you turn this 1,3 BPG into 3 phosphoglycerate, okay? So you turn that into this, and then eventually you turn that 3 BP into pyruvate, that is 3 carbon, okay, and some ATP, right? So that is a whole cycle right there for you, right? I memorized this, and yes, I remember this because I remember this. So we have this, we have this, we have this, we have this, and we have this, right? So what's happening here? We have this 1,3 BPG, right? This enzyme right there. Now, as you can see, we have this 2,3 bisphosphoglycerate, 2,3 BPG as well, right? Now, where is this 1,3 BPG? Now, it is normal glycolytic intermediate, right? On the 6th step, it is present, right? Let's go back to the glycolysis. Where are you, glycolysis? On the 6th step, we have an enzyme called GAPDH, which is glycerolaldehyde 3-phosphate dehydrogenase, removes the hydrogen from G3P and puts it on NAD, and in this process an inorganic phosphate is also used. In the end, we get 1,3 BPG plus NADH, okay? And later this 1,3 BPH in step number 7 is converted to 3 PG, and we get an ATP at step 7. And this is done by an enzyme called phosphoglycerate kinase, right? And you do this by doing a substrate level phosphorylation, a kinase, right? And it puts a phosphate on ADP and turns it into ATP. That's step 7 for you. Let's come back to our main question. So our main question is about now 1,3 BPG, right? We have this enzyme right there. Now, how is 1,3 BPG formed? All right, I already told you, right? With this GAPDH and everything, right? Now, we have this enzyme formed now, right? The thing is that 1,3 BPH, right? This is very special. And now you would ask me, well, why is it special? Because the thing is, it contains phosphate at 2 locations, at first carbon and at third carbon. So it has 2 phosphate groups, okay? Now, what normally happens is that 1,3 BPH continues through glycolysis, right? And 1,3 BPH goes through this 7th step, which I already told you. This 1,3 BPG goes through phosphoglycerate kinase, and then we have 3 PG, right? And ATP, right? Now, what's the most important event happening here? The ATP production at step 7 is very important, and we call this ATP production substrate level phosphorylation. I already told you about that, right? Now, the thing is that but RBCs do something weird and strange. What RBC do is that, let me just put it in a different way. Do RBC always send 1,3 BPH into ATP production? That's my question. Turns out, no. Sometimes they choose a different pathway, right? What happens here is that we have this step 6 product, right, that is called 1,3 BPH. What RBC does, now we are going into a different direction, not in glycolysis pathway. We are going to a different pathway. Here, what happens is that, so here, what happens is that you have this 1,3 BPG, then we have a mystery enzyme, okay? I'm gonna write it as RBC enzyme. And this mystery enzyme gives us what? Gives us 2,3 BPG, right? Now, why would the RBC leaves the glycolysis? First of all, because we are getting, in 3 PG step, we are getting, in 7th step, we are getting ATP, right? Why would the RBC leave this glycolysis pathway? Because sometimes oxygen delivery is more important than ATP production. Now, let me answer this. This special enzyme is actually called bisphosphoglycerate mutase, right? Now, let me name it for you. This is called bisphosphoglycerate mutase. It's a mutase. Now, let me tell you what's really happening, right? Let's break this part first of all. Bisphospho means we have 2 phosphate groups, okay? Let's break this word from here, right? Bisphospho means we have 2 phosphate right there. Glycerate, the word glycerate means 3 carbon molecule that comes from glycolysis or are derived from glycolysis. So that is glycerate. We have 3 carbon molecule that are coming from glycolysis, okay? And then we have a word called mutase. What do you think mutase means? Mutase means something that moves the functional group within the same molecule, okay? So mutase means it changes the location of functional group. So functional group translocator, I should say. It changes the location of what? Functional group, right? It doesn't add any phosphate, it doesn't remove any phosphate, it just rearranges that phosphate molecule, okay? Not phosphate, functional group, exactly, functional group, not phosphate. Now what does this enzyme actually do? This enzyme converts 1,3-BPG into 2,3-BPG, right? It's happening right there in front of you, right? Now you want to notice something carefully, right? We at this point we had phosphate at first position, but now we have phosphate at second position. Instead, the position, like right now what just happened was the position of the phosphate changed, and that's why this enzyme is called mutase, okay? So a lot of people get confused between glycerate mutase and bisphosphate glycerate mutase. Bisphosphoglycerate mutase is different enzyme, and phosphoglycerate mutase is different enzyme, okay? Phosphoglycerate mutase, it's in glycolysis. It changes that 3P, that is 3-phosphoglycerate, into 2P. Wait, let me go to glycolysis and let me show you, right? So we have this step 8. On step 8, we have this enzyme called phosphoglycerate mutase. This moves the functional group from 3 to second carbon, okay, position. And this enzyme is different than this enzyme called bisphosphate glycerate mutase. This one changes the phosphate from first to second, okay? They are different enzymes, okay? Totally different enzymes. Now the thing is, why would you want to produce 2,3-BPG, right? Why do you want to sacrifice ATP that will come from glycolysis, right? Because oxygen delivery is more important than maximizing ATP in a lot of conditions. What happens is that 2,3-BPG actually binds to this deoxygenated hemoglobin, right? And the thing is that this 2,3-BPG, it actually stabilizes the tense state of hemoglobin, right? Which leads to hemoglobin affinity for oxygen decreasing, right? So it actually decreases the affinity of hemoglobin, making it easier for the hemoglobin to release it in the target tissue, okay? What's happening here is that it does something amazing. It stabilizes. I will tell you what is really happening. Stabilizes what? Stabilizes the T, or we should call it tense state. Tense state of hemoglobin. Now what later happens is that this tense state is stabilized. Once the tense state is stabilized, we have the hemoglobin affinity of oxygen, right, towards the oxygen actually goes down. So affinity drops, and it's way easier now for hemoglobin to drop off that O. Take it, okay? So this is exactly what's happening here, right? So let's break the system a little bit. Let's just suppose what's happening here is that, let's break the system a little bit. RBCs had mitochondria. Let's just imagine that. What would happen? They would consume the part of oxygen that they are supposed to be carrying, right? That's why oxygen don't have mitochondria. If someone asks you basic question like, why RBC don't have mitochondria? Well, RBC, if they had mitochondria, they would consume the oxygen that they are supposed to carry, right? Suppose if RBC couldn't make 2,3-BPG, the question is, would they still carry oxygen? Obviously, because the affinity will be still up. But they would have difficult time releasing that oxygen to the tissue, right? Hemoglobin will hold onto the oxygen more tightly. And suppose 1,3-BPG always become ATP. Would ATP increase? Absolutely, yes. Would the lifespan of the ATP increase? Would the lifespan of the RBC increase? Of course. Maybe it will go to 150 days. But is that good for you? Because I don't think so. Because 2,3-BPG production would decrease, right? And oxygen unloading will be worsened, right? So RBCs intentionally sacrifice these ATP to optimize oxygen delivery, right? Suppose this bisphosphoglycerate mutase, this enzyme, right? This enzyme never existed. Would you have 2,3-BPG? Obviously no. So again, the unloading part of the oxygen would be very difficult, right? So that is actually what 2,3-BPG does, and that is that, right? This is it. This is it actually. So 2,3-BPG is an enzyme that goes and it stabilizes this tense state, right? So you need this 2,3-BPG for unloading of RBCs, okay? Unloading of, not RBCs, unloading of oxygen from the RBCs. That's very important. I think that's it for today. And I hope you understood this whole little thing, right? So that's it.